Although there's a ton of excitement these days around LLMs and AI agents, I'm more excited about the recent innovations in text embeddings. We saw these in the previous video of this series where we used text embeddings to implement a RAG system to improve an LLM. In this video, I'll discuss text embeddings in greater detail and share two simple yet high value use cases, namely text classification and semantic search. And if you're new here, welcome. I'm Shah. I make videos about data science and entrepreneurship. And if you enjoyed this content, please consider subscribing. That's a great no-cost way to support me in all the videos that I make. There's a fundamental challenge in trying to analyze text. Put one way, text isn't computable, meaning we can't do math with text in the same way that we do with numbers. For example, say you go to a networking event and you're talking with other professionals in the data space. If you wanted to summarize the typical height of every person at the networking event, this is something that would be pretty straightforward. All you would need to do is measure the heights of everyone at the networking event, and then you can summarize these heights using something like an average. And this is something that you can easily compute using a calculator, Excel, or your favorite programming language. However, if you have the job descriptions of everyone at this networking event, summarizing everyone's roles wouldn't be as straightforward because there's no Excel function or mathematical operator that allows you to put in text and generate a summary. And so this is where text embeddings come in. And put simply, text embeddings translate words into numbers. So if we have those same job descriptions from the networking event, translating these descriptions into text embeddings would look something like this. For every single description here, we would map it to a set of numbers. But these aren't just any set of numbers. These are numbers that capture the inherent meaning of the text. In other words, text embeddings translate words into meaningful numbers. And one way we can see this is take all those numbers from the previous slide and use them to visualize all the job descriptions. And so that would look something like this, where the numbers that we generated in the text embedding define the location of each person's job description. We can see the data analyst in retail with 5 years of experience is somewhere here, and they are located next to a freelance data visualization specialist with 4 years of experience. However, these people are relatively far away from this guy who is a data architect with 15 years of experience. And so this is the way that text embeddings capture the meaning of the underlying text. Namely, job descriptions that are similar will be located close together, while job descriptions that are very different will be located far away from each other. From this view, the BI analyst in hospitality early career is very different than the data architect with 15 years of experience. So if you've used ChatGPT in the past, the thing that might come to mind is, Shah, why should I care about these text embeddings and translating text into numbers? Can't I just pass all my text to ChatGPT and have it figure out what I'm trying to do? And the answer is yes. There are many tasks that don't require these text embeddings, and they're much better suited for ChatGPT. For example, if we wanted to summarize the 8 job descriptions from the networking event, it would actually be super simple to pass all these to ChatGPT and generate a summary. However, if you have a use case that's not just some one-off low-stakes task, but is something you're trying to integrate into your product or a website or some broader production-level software system, then you'd probably want to at least consider using text embeddings before running off and building an AI agent. And the reason is, if we're talking about AI assistants, it's really the early days for this type of technology, and there are still a lot of things that we don't understand about using these large language models in this way. Another downside of using an AI assistant for your use case is that there's a major computational cost associated with running these large-scale models. Another downside is the inherent security risks that come with building LLM-based applications. And so there's a nice list of top 10 LLM security risks at reference number 3, which I recommend you check out. For example, these are things like prompt injection, which are maliciously crafted prompts which get the LLM to expose private or confidential data or disrupting some expected decision-making pipeline. Finally, responses from these LLM-based systems might be unpredictable and prone to hallucinations. hallucinations where the system generates fictitious or unhelpful information. On the other hand, text embeddings have been around for decades, and there are several past example applications that we can look to help guide future applications and use cases. Another upside of using text embeddings is that they have a much lower computational cost and thus financial cost than using an entire large language model. Another is that there are far fewer security risks associated with using an embedding model compared to a large language model that users can access through a chat interface. Finally, the responses are more predictable because, every word or piece of text will generate a deterministic set of numbers. So there's no randomness in this process. Now that we have a basic understanding of what text embeddings are and why we should care about them, let's see how we can use them for a practical use case. The first use case I'm going to talk about is text classification, which is the process of assigning a label to a piece of text. For example, if we were to take all the people from our networking event and their associated job descriptions, a classification task could be trying to determine which people are data analysts and which people are not data analysts based on their respective job descriptions. So that might be pretty simple here because anything to the left of this blue line we could label as a data analyst, and anything to the right we could label as not a data analyst. However, text classification is a broadly applicable use case. Some other situations might be classifying emails as phishing attacks versus not phishing attacks, or classifying credit applications as fraudulent or not fraudulent. And the list goes on and on and on. With this high-level understanding, let's see what text classification with text embeddings looks like in code. So in this example, I'm going to take a data set of resumes and try to classify them as either data scientist or not data scientist based on the content of each resume. The code in the data set for this example is freely available on the GitHub repository linked here. Feel free to steal this code as a jumping off point for your own use case. So the first thing we're going to do is import some helpful libraries. Here we're going to use OpenAI's text embeddings. To use OpenAI's embedding models, we'll need to use their API, which requires a secret key. If you're unfamiliar with the OpenAI API or how to get a secret key, I walked through that step by step in a previous video of this series. Next, I'll import pandas, numpy, and matplotlib. So we'll use pandas to structure the data, we'll use numpy to do math, and we'll use matplotlib to visualize things along the way. And then finally, we will import some things from sklearn, specifically their random forest classifier, which is just a machine learning technique for doing classification, and then the ROC-AUC score, which is a way to evaluate a classification model's performance. Here, we're going to import our data from a CSV file, and the CSV file is available on the GitHub repo. Just one note here, the data used in this example and the next example were actually synthetically generated using GPT 3.5 Turbo. Although I don't like using synthetic data in these code examples, I went with the fake data set here to avoid any privacy issues in using real people's resumes. Nevertheless, this example is instructive in how you can apply text classification to text embeddings. Next, we're going to generate our embeddings. So here I'm going to define a function to do this for us. Basically, what this function will do is take the text and my OpenAI secret key, and it'll spit out the text embedding object. The way we do that is we set up communication with the OpenAI API, and then we just make an API call by passing it the text and specifying which model we want to use. This is one of OpenAI's newer embedding models, and it has about 1,500 dimensions. So each piece of text is going to be translated into about 1,500 numbers. And then they have another option which has about 3,000 numbers, and that's called text embedding 3 large. And then the function will return the API call response. And then here, for every resume in our data set, we can generate the embeddings in one line of code. Then we can extract these text embeddings and store them in a list in this line of code here. Then we'll store all the text embeddings into a new pandas data frame called dftrain. So here I'm automatically generating column names. So these column names will be embedding underscore 0, embedding underscore 1, embedding underscore 2, all the way up to embedding score like 1535 or something, however many embedding dimensions there are. Then we can create the pandas data data frame in one line of code. So just by passing in this list of text embeddings and the column names. And then I'm going to add one more variable to this data frame, which is a true false, a Boolean variable, which indicates whether that row is associated with a data scientist's resume or not a data scientist's resume. And then we can split our variables into a set of predictors. So X will be all the text embeddings for every one of our resumes. Y will just be the true false, is data scientist, is not data scientist variable. And then we'll pass this to the random forest classifier to train a model. So just in one line of code, we train our classifier. We can print the accuracy and AUC value of the model applied to the training data. So the output here is 1, indicating perfect performance of the model on the training data, which is super suspicious. So let's evaluate the model on a different data set. Here we're going to load in a testing data set. So this is also available on the GitHub repository. Here we're just repeating the same steps as we did for the training data. We'll read it in as a pandas data frame. We'll generate the embeddings in one line of code. We'll extract the embeddings as a list. Then we'll create a new pandas data frame for the testing data. And then we'll create a target variable of is data scientist for the test data. And then we'll split it into a set of predictors and the target variable. With that, we can simply evaluate the model on this new data set with these 2 lines of code. And we see the model still has very good performance on the training data. However, before we kind of celebrate, the model is still likely overfitting here. And there are 2 reasons for that. First is we have 1,537 predictors, but only 100 records. In these situations where you have a ton of predictors and very few examples, it's not hard for the model to memorize the training data and overfit to it. Secondly, the training data and testing data were generated in identical ways using GPT 3.5 Turbo. And so this is one of the downsides of generating synthetic data, is that there are going to be artifacts in the data generating process which may create similarities between our training data and testing data that won't be relevant to resumes from the real world. So while there are many ways we can solve the overfitting problem, in this situation, the best thing would be to, 1, get many more examples of resumes. So 100 resumes isn't going to cut it. Probably want closer to 1,000 or 10,000 resumes. And then second, if you want to use this model on real world resumes, you should train it on real world resumes. Moving on to the second use case of semantic search. The big idea here is that semantic search returns results based on the meaning of a user's query, in contrast to keyword search, which looks to match specific words or phrases in the query to a set of search documents or web pages. And so the way this works in the context of text embeddings is that, say we have a query like, I need someone to build my data infrastructure. If we were to take everyone from our networking event once again and embed their job descriptions in this concept space here, the way we can do semantic search is we can embed the user query into this same space. And if we were to do that, the query might sit somewhere over here. Then if we wanted to return search results, we could look at the 3 nearest job descriptions and return them in our search results. And for this particular query, keyword search may not work so well because there's no mention of the typical role that would be able to build a data infrastructure, namely a data engineer. However, semantic search is able to connect this task of building a data infrastructure to things like data engineer, or building data pipelines, or ETL process, or building a data model, and other related skills and activities to building a data infrastructure which may not share the same exact wording. Here we're going to use text embeddings to implement semantic search in exactly the same way as we saw in the example on the previous slide. So we'll use the same data set as in use case 1, and what we'll do is we'll take a user query such as, I need someone to build my data infrastructure, and return resumes in our data set which match that user's query. Again, we're gonna import some handy libraries. We have NumPy and Pandas, and next we import sentence transformers, which is actually an open source library with many embedding models that you can use completely for free. So no need to get an API key or pay to make API calls to OpenAI's API. Next, again, we're going to import things from scikit scikit-learn, namely this PCA function, which allows us to do dimensionality reduction. And if you're unfamiliar with PCA, I actually talked about this in an old video, so I'll link that on the screen so you can check it out if you're interested. And then we'll import this distance metric function, which will allow us to measure the distance between the query and all the different resumes in our database. Finally, we'll import matplotlib to visualize some things. Okay, so here we'll read in the data in the same exact way as before. So we'll read in this resumes_train.csv file. One thing we'll do quickly is that this CSV file has a column called role, and then there are a handful of different roles, but there's one of them that's a sentence. It's not a specific role. We'll just relabel all those elements as other. Next, we're going to generate the embeddings. So the sentence transformer library makes this super easy. So all we do is import the model, and then we can use this .encode method to pass in all the resumes and generate embeddings for all of them. And so there are several embedding models to choose from in the sentence transformers library. Here I use this one, all-mini-lm L6v2, which was specifically designed to do this semantic search task. If you're trying to do text classification or some other NLP task, I would check out their pre-trained models in their library and try to tailor the model for your specific use case. Next, we can visualize all the different resumes and roles in this embedding space in the following way. What's happening here is that I used PCA to reduce the dimensionality of the embedding space from 384 down to 2, so it can fit on this 2D plot here. And since this is a lot of code to do the data visualization, I don't want to show it here, but it's available on the GitHub for anyone who's interested. Here we can see that even though we're flattening this embedding space from 384 dimensions down to 2, we can see that the different roles such as data scientist, data engineer, machine learning engineer, AI consultant, data entrepreneur, and other, they tend to be localized pretty well in this visualization. So this is a good sign, because if we have a query that aligns with a data scientist, it will likely be close to a lot of data scientists that can fulfill that role. Next, we can define our query. So we'll use that same, I need someone to build out my data infrastructure, and then we can encode it in the same exact way as we encoded the resumes using this .encode method. That'll generate a one-dimensional NumPy array called query embedding. Then we can compute the nearest neighbors. And so the way we do that is first I'll define this dist object, which is a distance metric, and then we can compute the pairwise distances between the query embedding and all the resume embeddings in this embedding array that we defined earlier. All these pairwise distances will be stored in dist_array, which is a NumPy array of the distance between the query and every single resume in the dataset. And then we can use this argsort function from NumPy to sort all of the distances in ascending order. Note that this isn't sorting the dist array. It's actually doing two things. It's sorting the dist array in ascending order and then returning the index of each of those elements. So the first element's not going to be the smallest distance value itself. It's going to be the index of the smallest distance value. That's all we need to do the semantic search. So what that'll look like is if we want to print the roles of the top 10 results, we can go back to our original df resume data frame, look at the role column, and then we can just return the first 10 elements in this dist array sorted array. That'll look like this. So the query, I need someone to build out my data infrastructure, returns a ton of data engineers, which is a good sign because those are the people that will be able to do that. Another thing we can do is to look at the resume of the top result. And so we can do that in this way. We go back to our df resume data frame, look at the resume column, and then return the resume that corresponds to the first element in this idist array sorted array. And so the resume looks like this. Just reading through this, highly skilled and experienced data engineer with a strong background in designing, implementing, and maintaining data pipelines. Proficient in data modeling, ETL processes, and data warehousing, adept at working with large data sets and optimizing data workflows to improve efficiency. And so notice that nowhere here does it say built data infrastructure, but it does say all these things that go into building data infrastructure: designing, implementing, and maintaining data pipelines, data modeling, ETL processes, data warehousing, scalable data pipelines, optimize ETL processes, data architecture. So there's so many buzzwords and so much jargon in this space, and just matching keywords together may not be super helpful. But when you use text embeddings, which captures the underlying meaning of the text, it tends to give good results. Visualizing these queries in the embedding space, it'll look something like this. So that same one, I need someone to build out my data infrastructure. We see that the query is pretty close to all the data engineers, which is a good sign. Another one is project manager for AI feature development. So this one tends to be closer to the machine learning engineers and the AI consultants. And it's kind of like on the border between the two, which makes sense because you're going to need an ML engineer for the feature development, but you probably want an AI consultant for the project management side of the project. And so probably a mix of those two skills will be best. And then finally, a data engineer with Apache Airflow experience. Pretty close to the data engineers, but it also seems close to this other category, which is just randomly generated resumes. Okay, so before celebrating, I want to kind of zoom into this particular query here, data engineer with Apache Airflow experience. For this simple semantic search example, it seems to struggle with specific search requirements, such as I want a data engineer, but I specifically want them to know Apache Airflow. And so when I pass this into the semantic search system, only one of the top 5 results had Airflow listed on their resume, and of the top 5 it was the third one that had it, even though there were 3 other resumes in the data set that had Apache Airflow experience. And so this example illustrates that semantic search isn't better than keyword search in all situations. Each of them has their pros and cons. And so if you want to build a robust search system, you'll likely want to employ both keyword-based search and semantic search to get the best of both worlds. Which brings us to a few additional strategies for improving a search system. First is hybrid search. And so this is exactly what I just mentioned, which is bringing together keyword-based search and semantic search. While there are many ways we can bring these two approaches together, a simple method would be, given a user's query, apply a keyword-based search to it. So you'll filter down the search results based on specific words in the query, such as data engineer or Apache Airflow. And then from those results, you'd apply the semantic search. Another option is to use a re-ranker. And so a re-ranker is a special type of model which takes in a query in a document, for example, and it spits out a similarity score. Notice that this is an alternative way to compute the similarity or the difference between 2 pieces of text. Common way to use a re-ranker is, let's say you use your semantic search system and you return the top 25 search results from the semantic search. You can use the re-ranker to take those 25 search results and compare them with the query to do an additional ranking. And empirically, this seems to have pretty good results, especially when integrated into a RAG system. And then finally, you can fine-tune an embedding model for a specific domain or use case. One of the downsides to these embedding models is that they tend to be trained on a large corpus of text. So while this makes them very good at general purpose tasks, they may fall short in specific domains where there may be heavy use of jargon. For example, if I wanted to further improve this semantic search system, navigating all the jargon of data engineering, ML engineering, and data science, I could additionally fine-tune the embeddings on this type of text. So if you enjoyed this video and you want to learn more, check out the blog published in Towards Data Science. And although this is a member-only story, you can access it completely for free using the friend link in the description below. While this does bring us to the end of the LLM series, at least for now, if there's anything that wasn't included in the series, please feel free to drop that in the comments section below, and perhaps the series will be resuscitated once again in a few months. And as always, thank you so much for your time, and thanks for watching.